this evening then is a brief history of timekeeping. Now, in the spirit of trying to keep it brief, I literally cut this talk in half. I'll explain where that comes from in a minute. So, where do we start with timekeeping? Hopefully with a mouse that's going to work. There we go. So, the most obvious measure of time is the passing from light to dark to light again with the rising and the setting of the sun. And that was probably the first way that we ever had of measuring some sort of aspect of time. Even somewhere as cloudy as Aberdeen, the day-night cycle is as plain as, well, as plain as day. So, yeah, I had to get that one in there. So that was the first way that we started to recognise the measuring of time. And it's been such a fundamental part of evolution that, well, and with other animals, that we have circadian rhythms. The 24-hour clock is actually genetically embedded into our genome. So the things like changes in body temperature, hormone levels, the way our body processes, the functions that it goes into, are controlled in some parts at a genetic level by the 24-hour clock which we're used to. That being said, we can mess with that. These days we have a lot of lovely little digital devices which give off lots of blue light, which confuses our brains and starts to mess up our sleep cycles. We get increasing numbers of cases of insomnia and things like that. We can mess with it further. Submarine crews, for example, on a submarine, particularly a nuclear submarine, they run 3 shifts of crews. They run an 18-hour day. So you have 3 crews, you're either on your 6 hours of work, your 6 hours of rest, or your 6 hours of sleep. And then every 6 hours, another batch of crew wakes up to start their day. But it means every 18 hours, you have a new day, which means if you go away for what might have been a month in normal time, it feels much longer than that because you experience more than the usual number of days. Now, most of human history, the daily and annual cycles of time have been enough to get us by with what we needed to know. This is where that talk that I mentioned splits. I'm going to be looking at the days and everything less than that, and everything that's more than that is maybe a future talk. But it's a separate one because otherwise it was going to be a not so concise history of time, and the brief bit might not have been very accurate. So, we've got a 24-hour clock. The easiest way of then subdividing that, sort of, was the tides. Tides happen on average every 12.5 hours, or 12 hours and 25.2 minutes, if you want to be a bit more accurate. And so it does give you a way of breaking the day down. But the fact that it's that bit over the 12 hours means it's not reliable and predictable on a day-to-day basis. You can't say I'm going to be doing the same thing at the same time, because it's going to start to drift, to become later and later by 25.2 minutes for each tide. But advanced civilizations needed some sort of way of recording time, of breaking down what they were going to do, keeping schedules, making plans, doing those terrible things that we would now call Gantt charts, of knowing what they needed to do by when, so that they could survive, and that they could then have politics and all that sort of stuff. So here I have a picture of the Egyptian pyramids, but this isn't the most ancient of civilizations to be dealing with time. The ancient Babylonians, Sumerians, Mesopotamians, it all came before the great Egyptian empire, all were concerned with how they record time, both in terms of days and years, and subdividing their days. So this is really the first way that this was done. This is an obelisk. Now, technically, this is actually the Luxor obelisk, which they stole and took to France, so it's actually in Paris now. A lot of Egyptian artifacts are not in Egypt, and that's a bit of a bone of contention for the Egyptians. But this was the first way that you could measure time. The obelisk gave a shadow. The weather's a bit more predictably sunny in Egypt than it is here, and you could track that shadow through the course of the day. So you could say to your slaves, I want you to finish this task by the time the shadow gets to this point, or there'll be trouble. So that was the first way that we measured time. That then got formalized and worked a bit further as the sundial. So here we have a very, very old sundial that shows the day being broken down into 12 parts. Now 12 is an interesting number. Now in Western cultures we're used to dealing with a base 10 number system. The easiest way to talk about that is that it's due to our fingers and thumbs. If you want to go beyond 10, well, you take your shoes off, but you're still a bit limited. The Egyptians went with 12. Now 12 is a much better number than 10 because it's more naturally divisible. So 10 divisible by 1 and 10, well, that's kind of a bit pointless, but besides that it's only divisible by 2 and 5. 12 is divisible by 1, 2, 3, 4, 6, and then 12 as well. If you're happy to go to halves, 8 also fits in. Okay, so it's not too hard to stretch 8 getting into the numbers of 12. So it's a very useful number. Now the way that you count that on your hands is you use your 4 fingers, each having 3 knuckles. You have point 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So you can use your knuckles as a rudimentary way of counting things, but it's not the most advanced way, and we'll come more onto that in a moment. So they had this base 12 number system that they used for a lot of things. Now the other reason that 12 seems to have been popular is if you take the year as a whole, you fit 12 lunar cycles or phase cycles into a year. There's a bit of loose change, but we'll come back to that another time maybe. So 12 was a very powerful number. It had a very practical use in terms of division, had a meaningful use in terms of the number of lunar cycles in a year. So the one problem with this is this sundial doesn't give you fixed amounts of time. It divides sunrise to sunset into 12 parts. But as we go through the year, the length of the day, not in terms of the entirety of the day, but the hours of daylight, changes. So during the summer, you have long hours, and during the winter, you had short hours. But it was still workable because most of the work had to be done during the course of the day, so at least you could divide that up and allocate your tasks accordingly. Now, that's fine if you're trying to keep track of the day, but obviously that's not going to work at night time, so we needed a different system for that. And that's where one of these comes in. This is, now I don't know how to pronounce it, a merkit, or something like that, what most of us would just call a plumb line. Short version, it was a piece of string with a heavy mass at the end that gave you a nice vertical line. And what you could do is you could fix that from a certain reference point and look for the evening sky moving, or appearing to move, against this reference line. So they divided the sky up and had these reference stars, fairly evenly spaced across the sky. And you knew what time it was by this reference star coming up to and then crossing this line that you had set. Now, you could use a plumb line, you could use a fixed structure like a wall or door and various other things, but this merkit was quite popular because you can just hold it wherever you need to be, you just hold it up and you've got this vertical line that you can then be using. Now, this then was a bit strange because we have our day divided into 12, we have our night divided into 12, and I think, oh, that sounds great. Except the day hours are varying in length according to the seasons. The nighttime hours are fixed. Now, they are fixed, but they're also not of equal length, because they wanted nice bright stars that were easy to identify. So you have some hours being shorter or longer than each other, but being varying in, unequal numbers of hours that were fixed in length versus a day of varying hours. So the two didn't quite match up perfectly. So the next piece of technology was, of course, water. So the Greek astronomers, now there was a lot of, borrowing of ideas from the ancient cultures in Egypt and Mesopotamia by the Greeks and the Romans. And the Greek astronomers figured out they could use drips of water as a timing device. Now, if ever you've been irritated by a slightly... Everyone laughs so easily at that one. Irritated by a dripping tap, you know it's that annoying, regular sound. Now, it's regular for us because we live in a modern culture where we have high-pressure water provided to our house. So there's a, as a pseudo-infinite supply of water. It's not going to run out, it's not going to change in pressure, it just keeps coming. And the tap therefore keeps dripping and dripping and dripping. So our dripping taps would actually be better timekeepers than the early water clocks, because the early water clock was literally just a big basin with a small hole in the bottom of it. Now, if ever you've had a small hole in a bucket or other basin, when you've got it full of water, that pressure means that the water comes out the bottom at a greater rate. As that drains lower and lower, the pressure reduces and your stream of water slows down. So there was two ways around this. Either you had a set of markings in whatever container that you had that varied their spacing to accommodate the varying flow rate, or sometimes you actually had the markings within the container itself so that you could look at the top level of the water and again vary the spacings accordingly. There are various ones of these where they've actually got multiple sets of these varying spaces because they've got their summer hours versus their winter hours and ones in between. That was eventually improved on by having multiple sets of water. So if the water is changing its rate of flow based on the pressure due to the depth, all you need to do is make sure that your top basin is always full. So here they just had to keep, so they generally had a bucket up here that was even bigger, had even more water than would fit into this second one. It was pouring more water into this one than it could cope with. It was spilling out the top, and that meant it was always at maximum height, always at maximum pressure, always delivering a steady flow of water. Now, these clepsydra were actually used in courts of law. These were the timing devices. If you had a particular case to make it fair, the lawyers for the accused and the lawyers for the defence would, the accusing and defending lawyers would have equal amounts of time. They would have a clepsydra each. If it was a particularly large case, they might have a certain number of clepsydra. And the advantage of these, you could say, right, we're going to take a little break, and you just put a bung in, and you can pause time and know that you've still got whatever allocation is left to you. So this gave us one of the first ways of counting time, processing it, rather than just observing it changing through the day. That was then refined even more by Ctesibius, or something. I can't really pronounce his name very well. He was an everyday kind of guy. His dad was a barber, and as he grew up, he wanted to help in the barber shop. So he made things. He made a stand for the mirror that was flexible, would allow the mirror to be rotated in direction. Now, that doesn't sound that impressive until I tell you that this was about 250 years BC. Okay? So he was a genius. He invented lots of these little bits and pieces that just improved their day-to-day living. And he refined this clepsydra into a full-blown water clock. So it was him that came up with this idea of always keeping the top, or keeping a reservoir at full height by having an excess of water at all times flowing into it. But then he took things further. He started to invent what we would think of as actually mechanical clocks. So here we have a reservoir of water with a buoy, or a buoyant object in it. On the end of that is a rod and some sort of figurine. And as the water level rises here at a constant rate, then the figurine rises at a constant rate. This figurine then has a pointer that goes up a scale to show you on the hour or on the half hour and divisions such as that. This then meant you could actually record in a continuous fashion longer amounts of time. So these started to span a full day, going from the day cycle into the night cycle and then being able to be reset the next day. They could even go further. Because he was such a whiz with mechanics, you might notice there are various cogs down here. He actually had it that it would spiral, and this cylinder was also a calendar. So he could actually track the days as well as tracking the time, all with this one machine. Now, not to be resting with that, he took it one step further. He thought, right, I've got water. I can use this water to actually do mechanical work. I know I'll pump a bellows. Well, if I can pump a bellows, what can I do? I can put it through a whistle. Well, what kind of things whistle? Birds. So he invented the cuckoo clock around 250 BC. Okay? Now, going off script a little bit, Archimedes then took that and took it even further, and he then had the first bells in clocks. So you actually had the gears, actually, the teeth of the gears would actually pick up rocks or marbles and actually tip them over and drop them onto a bell to give the chiming of bells. Anyway, so astronomers. So here's Anaximander, one of the great exponents of the, gotta get around the right way, the heliocentric model back in the day. So he was actually before Stathidius, but he was doing lots of astronomical readings, and he was struggling with the limitations of his measuring devices, as all the astronomers were at the time, because they were getting the understanding of the maths, they were getting the understanding of how the sky worked, to some extent, but they were limited by the precision to which they could make their measurements. So it was a big push from the astronomers to be able to take things further. I'm missing a picture here. Anyway, they did that. Now, unfortunately, a lot of the knowledge is lost. They had tons of knowledge, they stored it in libraries, which then got burnt down. The greatest of these was the library at Alexandria. When they were furnishing this library, they literally sent captains out on boats to explore, and if they came back with any manuscript they did not have in the library, they bought it by the weight. So you'd get captains going off. I'm not going to say how they acquired these manuscripts, but they did. And they came back with loads and loads of these manuscripts. They brought them back and they sold them. And the library then translated them, stored them, and it was a huge wealth of information. And eventually, well, actually, not eventually, it happened a number of times. Bits of it got burnt down until it fully got sacked and completely destroyed. And there are huge amounts of knowledge that are just gone. In that was probably knowledge to do with a very particular device. Now, this could be its whole talk in its own. I'm not going to go there, though. This is called the Antikythera mechanism. There were some pearl divers off the coast of Greece, and there was a storm coming, so they took refuge in a cove. And when the storm had passed, they thought, oh, well, we've kind of wasted the time. Well, we'll just go, we'll see what's here. Why not? So they went down and found a shipwreck. They thought, awesome. So let's see what's here. They went and they found various things, but they found this device, which to most people kind of looks like clock gears, except for the fact that this was from between 150 to 100 BC. This is a mechanical device. With a lot of figuring out, it actually turns out to be an analog computer. Okay? You think of an abacus, you do the moving, and you have to know what to do to be able to use it. This did the knowing for you, you just turned it. And this could keep track of months, could keep track of years, could keep track of leap year cycles, which are tied into the Olympics. So it was a really, really detailed, complicated device that did amazing amounts of calculation. That when they discovered this, there was huge debate. This couldn't have been this old. But they've done X-rays of it, they've done MRIs of it, they've studied in every which way that they can. Every time there's a new invention in technology, this is one of the things they pull out the cupboard and say, right, let's see what else we can learn from this. A hugely powerful device. If you are curious, just go onto YouTube. There are full documentaries about it. But the Antikythera mechanism, as it's known, was amazingly powerful. And it gives us a glimpse as to what the ancients were actually able to do. Now, part of how they could do that was they had taken the maths a long way forward. Part of that was just good old angles. A circle, 360 degrees. Now, a circle of 360 degrees, a bit of an odd number. Now, that comes from the Babylonians and Sumerians. They used to work in not a base 10 system, not in a base 12 system, but in a sexagesimal system, which is base 60. So, they counted in 60s. They had 60 digits before they would roll into their version of the tens. Okay? Now, you think, okay, that's just going to be awkward. But they were clever people. Now, the reason they chose the number 60 is it's a highly composite number. So it has a huge number of factors. So it's got 12. So it's got everything that 12 had. 1, 2, 3, 4, 6, 12. But it also has others. It fits 10, it fits 20, it fits 30, it fits 15. I've probably forgotten one of the others. So it has so many factors, it was really easy to work with. When you had something you had to pay tax on, you could do the fractional taxing relatively easy. If you had to divide the spoils between a group of people, you could do so relatively easily. None of this decimals that go on forever. Okay, it was much easier to work with. So, because they had these 60s, the 60s, we had 6 60s made up the circle, 360, conveniently again matching the days of the 12 lunar months, if you think of a lunar year, not too shy of the calendar year that we use now. So 360 was a very useful number. And the problem was that they wanted then to go smaller than that. So they went for the minutiae of that. So it had the primary minutiae, which was a degree cut into smaller pieces. 60 of them. Minutiae became minutes. So primary minutiae became minutes, and then confusingly, the secondary minutiae became seconds. So we have a degree divided into 60, divided into 60 again. So 1 degree is subdivided into 3,600 parts. So we can now deal with very, very small angles using number systems that are much easier to work with than the base 10s that we have to work with in our modern world. So they had this huge ability to work with the maths. They could measure things out. Now at this stage, this minutes and seconds were arc minutes and arc seconds. They were about angles, about geography, they were about the world. But they hadn't yet moved into time. They did have hours as a subdivision of a day. They had fractions of hours, but they hadn't gone as far as minutes because they couldn't know the length of an hour accurately enough to be able to divide that very easily. So, that then begs the question of how long is a day? Now, there's a bunch of different answers that you can give to this based on what you think that question is actually asking. So, what's the easy answer to this question? 24 hours. Okay, so that is one version of a day. Talk, what would be your answer to the Christmas quiz if this question was asked? Just short of that. Okay, does anyone know that?
56 minutes.
Okay, 23 hours, 56 minutes, and a few seconds. So just about 4 minutes less than the 24-hour period. To which those that don't know are like, what? Okay, so there's a reason for that. It depends what question you're actually asking. It depends how you define your day. Now, I could have gone for the trick question and just said, how long does it take for the Earth to rotate? So, rotate. Okay, that takes a certain amount of time. The Earth, now if I'd ask that question, a lot of people will say, oh, it's 24 hours. No. Okay? It's not. It's 23 hours and 56 seconds. No, 23 hours, get there again, 23 hours, 56 minutes, and a few seconds. So where does that difference come from? So, wrong way. Here we have a diagram. The yellow thing, unsurprisingly, is the sun. The blue thing, unsurprisingly, is the Earth, not to scale. Here at position 1 is where we have the Earth at a certain point in time. It then does a full rotation to end up at position 2. We know that it's done a full rotation because this red arrow, which could be you as an observer looking out, have done a full 360 degrees of rotation. But the Earth is not stationary, it is orbiting around the Sun. And as it orbits around the Sun, that means for the Sun to come back to being the same point for the observer, you have to do a bit more rotation. Approximating, in your cycle around the sun, in one day you'll have moved 1/365th. We'll approximate that as a degree. So you're a degree further around the sun, so that means you need to rotate for 1 extra degree to have the sun appearing back at the same position in the sky. Now these two things have two different names. We have the sidereal day, which is from going from position 1 to position 2. Sidereal coming from the Latin sidus, which is talking about stars. Okay? So based on the stars, it's 23 hours and 56 minutes. If you have a telescope at home, you can set it up on a certain star, and probably not in Aberdeen, but if you did come back the next night in somewhere with decent weather, you could come back 4 minutes earlier the next night and see the same object. Okay? If you don't have a telescope, you can do the same thing actually with a straw. You wait till there's a nice bright star that you can line up on a door frame or a windowsill through a straw, sticky tape it there, come back the next night 4 minutes earlier, and you should see your target back in that position. So this 1 degree for 4 minutes is then giving us our solar day. Now, the solar day, it does vary a little bit. So what we have is we have our sidereal day, 23 hours, 56 minutes and change. And then we have the mean synodic or mean solar day. Now, this is the mean because it doesn't stay the same. There's a number of things that actually affect the rate of a day on Earth. One of those is the fact that Earth follows an elliptical orbit around the Sun. It's not a very eccentric or not very elliptical, it's almost a circle, but a little bit of variation does mean at some points of the year we are closer and travelling faster around the Sun than other points when we're further away. But that's fine, we can factor that in, and actually that does come into play when we deal with time in very specific ways. But we also have random variations that we can't just factor in using an equation. These include tectonic activity. When we had the earthquake that caused the Fukushima disaster, there was a continental plate which did that. It receded down towards the Earth. Now, I did see someone earlier watching ice skating videos. And with the ice skaters, they start to spin like this with their hands out, and they bring their hands in to speed them up. Okay, you do the same in gymnastics or anything where you're trying to rotate. Something that's spread out will spin at a certain rate because of something called angular momentum. You contract that into a smaller shape around its rotational axis, it will have to speed up to maintain that angular momentum. It's basic physics, though the maths isn't always basic. So, that ice skater move is what happened to the Earth. It changed its shape, it got more compact, it sped up. So an earthquake led to a speeding up of the rotational rate of the Earth. Other factors that cause that. Over time, our planet is cooling. Okay? It formed, it was molten everything, and over time it has been cooling and contracting. So contracting, causing it to speed up. You then have other factors which tend to slow it down. We have tides, which I've mentioned before. As those tides go round, the big masses of water hit the continents, they bash into it. So actually it's kind of, the water is actually more sort of, or the tide is kind of stationary, the rotating Earth is coming under it and hitting it. And it's this collision is actually slowing down the rotational rate of the Earth. So bit by bit the Earth is slowing down due to that. Now that one is a bit more predictable, we can account for that one. But then we also get random variations. Depending on the weather, wind. Believe it or not, wind has the biggest day-to-day effect on the variation of the length of a day. So there are all these factors that come into play that cause these different variations. Because of that, we get out of sync. Clocks and sundials stop agreeing with each other. I'm going to skip over the next one. I'll mention it briefly. There is also a lunar day. If you base on a lunar calendar, you can look at how long that takes. On average, the moon takes 24 hours and 50 minutes to return to the same point in the sky, and the moon is used more in the sort of calendar kind of recording of time more than the day-to-day recording of time. Now, some people will know who this guy is. Actually, I'll throw it out to you guys again. Who's this guy? Anyone know? Galileo. Galileo Galilei. So, in 1583, he was an unknown student. He was just kind of one of many. One of the things that they had to do was go to a church service. Now, he must have got a bit bored, and was sitting there, and he was like, ah, those chandeliers. Big rope, big thing of candles, swaying backwards and forwards. I thought, interesting. And then he looked back at it later and thought, oh, it's swinging much bigger swings. But actually, is it different? So actually, when he was sitting there, he would sit there and he would time how long it would take to do a certain number of swings. Now, doing one is really hard to do, and you get really rubbish results because of the errors in trying to do that. If you do 10, you time 10, divide by that amount of time to get how long one took, you get a much better result. Do 100, again, a much better result. So he did whatever number it was, a much bigger result, and found out how long it took. And the same chandelier always took the same amount of time to do its swings, regardless of whether they were small swings or whether they were big swings. Think, okay, how did he actually do that? So he's sitting there minding his own business, timing. Now, this wasn't in the time where he could just take out his watch or his phone, so he didn't have any of the usual ways of measuring time. Does anyone actually know what he used as his timing device? Heartbeat. Took his own pulse. So he was taking his pulse, sitting there, using that as his indicator of how long it took to do these series of swings. So that's quite one way of trying to keep yourself awake during a boring session, is doing 2 sets of parallel counting. 1 counting his pulse rate, 2 counting the number of swings. So this intrigued him, and this is where he is often credited to be one of the pioneers, the fathers of science. Rather than being a philosopher of science that sat round arguing and talking, he went and did. He did experiments. Got a piece of string, put a mass on the end of it and swung it and had a look at what affected the rate of a pendulum. And he found out it did not matter if he had a little mass or a big mass, as long as he had the same centre of mass on that pendulum, then it would swing at the same rate. So mass didn't affect it. He also saw that the angle didn't affect it. So he actually quantitatively checked what he had measured in the church and actually done a series of experiments to say it doesn't matter if it's a small angle or a big angle, to a point. It does not matter. It will take the same amount of time to swing. Now, you probably have some sort of intuitive understanding of that now because we have lots of swings in our parks. I have a number of kids, and one of the parks we go to has a swing where it's only about that high, so it's a very short swing, and he goes tick, 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 and it's a right pain because you just have to keep doing this the whole time. Or you have the normal size swings, which is good because you can give a push, and then stand back, and then you give a push, and then you go out to a forest somewhere and someone has a rope swing. And you're like, hope it's safe, but anyway. They're often really long ropes, and they give you a really long, graceful, slow swing. So the length of the pendulum is actually the thing that determines the rate that that pendulum is going to tick at. So this was a very useful piece of information. Pendulums are only controlled, or the period of a pendulum is determined by the length of that pendulum. Not the angle and not the mass. He's like, that's so counterintuitive. You would have thought that the mass of something moving would determine the rate at which it moves, which then stemmed off into its own experiment of dropping balls off the Leaning Tower of Pisa. Okay, so this was sort of the inspiration behind that, because it just didn't. He's like, hang on, this seems so counterintuitive. I've got to go try it in a different setting. And he went and dropped 2 different size cannonballs, and they fell at the same rate, because mass doesn't determine the rate at which something falls. The aerodynamics does. Anyway, so he did a few other things to do with astronomy. I could spend a long time talking about him. But instead, I'm going to move on to this guy. This is King Philip III of Spain. This is in 1598. He set Spain's longitude challenge, a life pension for anyone that could accurately determine at sea the longitude of a ship. Now, for those that aren't familiar with longitude and latitude, latitude is how far up or down, or how far north or south from the equator you are. Okay? And longitude is how far east or west. Now, latitude is a relatively easy thing to ascertain. To do that, all you've got to do is find the angle between the horizon and something you know where it should be. The sun is really easy, and if you've got reliable data, the moon or stars can also be used. So it's relatively easy to find out that angle. The problem was east and west, that was really tricky. Now, why was Spain offering so much money? Because back in the 16th century, Spain was a force to be reckoned with on the seas. They were huge traders and explorers. The problem was they kept building ships, sending them off, and then having them crash into unknown lands. Or not knowing where they were and running out of food. Or just never coming back and no one knowing why. And so it was known that the reason for that was they didn't know their longitude. They would kind of keep sailing in a certain direction and sort of hopefully gently touch some land and think, oh, right, now we're going to go north or south from this point and figure out, find a city. Okay, that was kind of what they did. They were sailing largely blind in terms of longitude. So Galileo spent a reasonable amount of time pursuing this goal of trying to get this huge amount of money. He'd had a number of kids, he'd had a bit of debt by then, so he was definitely in the situation of trying to find ways of making money. Telescopes was something he sort of got, what should you say, distracted by, but timing was still a big thing for him. So he timed the period of the Jupiter moons, what we would now call the Galilean moons, although he didn't know that's what they were at the time. Well, didn't know they were moons, rather. Now, these took a number of days. Okay, between 1 and 8 days is kind of the range he was looking at. So he needed an accurate way of being able to time that, to be able to figure out where they were. So timing was still a large part of the science he was doing. But he sort of shelved his pendulum ideas. And someone else then picked them up. That guy was Dutch astronomer Christian Huygens. Okay, he did a huge amount of stuff. He really was a polymath. He did so many things so well. He improved telescopes, he invented forms of microscopes, and he invented the first working, what we would think of as a pendulum clock. Now, to build a clock isn't actually that hard. You need something to tick, or something that is regularly going to repeat. You need some way of counting those ticks, and you need some way of scaling that to whatever useful time frame you want that to be, seconds, hours, or minutes. So his invention, though, was 100 times more accurate than anything that existed at that day. Okay? 100 times more accurate. By which I mean it only lost about a minute per week. Okay? Lost or gained. So it was a huge upgrade to everything that was there. That meant for the first time, doctors had an external way of counting time to be able to take things like a pulse. So this was a really useful device. So we then jump ahead in time to when the UK ruled, not the UK at the time, Britannia ruled the waves. They had the same problem. They had all the ships which they were building, sending off over the horizon, and some of them would come back laden with goods and money and things like that. So that was great. They wanted more of this. They wanted to stop losing all their sailors, all their boats, because the rich people didn't like having to pay to build new ones. I don't think it was the sailors they were so worried about as much as their boats and goods. So in 1714, the government passed the Longitude Act, and this was a cash prize to anyone that could solve this problem. Okay, so we've jumped 150 plus years. This was still the problem of the day. John Harrison was a very unassuming man. He was son of a carpenter who learnt carpentry and then got into clockmaking. But he was really clever. Not because he learnt a lot, because he tried a lot, because he came up with new ideas. In some ways it was probably the fact that he wasn't traditionally schooled that gave him the advantage. He built a clock for one of the local well-to-do people to put in their stables, because that's what he did back in the day. And the problem was that these clocks, the grease would always gum up. It would stop working. So he thought, let's just get rid of the grease. So he built a clock entirely out of wood. There are no metal parts in his clock. And he had to do different combinations of hard and soft wood to get the mechanical properties he needed. But he then had also managed to find, had sort of recently come on the market, as it were, a very naturally oily wood from Africa. So these parts were self-lubricating. This clock has run for over 300 years without ever stopping, without ever needing to be lubricated. Okay? So this was a huge improvement. Now, when this longitude prize came up, he was, right, I'll have a go at this. And he did, and he invented the marine chronometer, much better than anything else that existed. And they took it out in boats and did tests, and the people awarding the prize were like, yeah, it's not bad. And so he took it away, and he refined it, and he refined it, and he refined it, until he kind of got sick of doing all this work, building these big clocks. He's like, right, as they do these days, let's miniaturize. And he came up with a pocket watch, or a small watch at least. So this is the entire clock shrunk down, but having all of the skill of these large clocks, but in some ways quicker to make because there's less materials, and they're also cheaper. Because it was one of the things that they had accused him of, oh, it's too expensive to make your clocks, we're not going to give you the prize. To be honest, I think it was the board of trustees for Longitude Prize were the hoity-toities, and he was a common man. And they didn't want to award this huge amount of money to recognise the success that all their peers that had been classically educated had failed to solve. So, this is his 1759 H4. This is his watch that he invented for people to be able to keep track of their longitude. James Cook, from the Western point of view, the discoverer of Australia, he said this was his most favoured possession. He would not sail without this H4, or his H4, after he'd first started to use it. It was so useful. It gave him the ability to be able to determine where he was accurately, and be able to survive so many trips to all these foreign and exotic places, until he went to a certain island and didn't survive that one, when he got a spear through. But that's another story. So, this watch was a huge deal. But still these well-to-dos, they didn't want to give him the prize. Like, oh no, let's grumble and find some reason of saying, oh, we're still reviewing it. Until actually the king at the time stepped in and said, oi, behave yourselves, give him the money, and they gave him some. But this was after decades of him improving clocks, of fighting to say, I have done what you have asked. Oh, you've changed the goals, I'll do that new bit as well. And they gave him the money, and then it was only a few years before he did die at the age of 81. So, that was longitude sorted. But all this work in building clocks developed particularly across Europe, where we have all these clockmakers, a particular set of skills to make precision machinery that would run efficiently. And so they started to build more complex machines. Steam engines were only possible because we had the skills from building clocks. This led to looms, led to mills, led to the Industrial Revolution. People left the fields to go work in factories. They were no longer working just by sunlight or paid by the task, and they did 14-hour shifts. They would actually clock in to work. They entered the drudge of the machinery of industry. But actually, because they were working, they were producing more things, they, in some ways, had more money available to them, and because they were asked to do such long shifts, tea and coffee became a thing. These workers, who were dead tired after these long shifts, started to spend some of their money to buy caffeinated items to give them that boost to get through the rest of the shift. So, our measuring of time has led to us appreciating hot beverages. But there was a bit of a feedback loop, because it meant those that were rich and powerful could afford to buy clocks, which meant they could control others and become more rich and powerful, and then buy more clocks, and it kind of went on from there. If you were poor, you couldn't afford a clock at this stage. You were stuck at a certain level. So all these sort of factories existed, people were slaves to the clock, and it was all based on about how much they could produce and how fast. But time had one more trick to play in this, that each city, and sometimes just big companies, had their own version of time. London had London time. Birmingham, Aberdeen, Edinburgh, Glasgow all had their own unique time. Okay? So, Dundee would be at a different time to what we have in Aberdeen. But that's fine, because Dundee's down there. And Edinburgh's even further down there. So we didn't really care. Until the world shrank. When we had railways and telecommunications started to make the world feel a smaller place. And particularly in the States, where it was a big, sprawling exploration of the country and railways going everywhere, they had junctions that were being used by multiple railway companies. And each railway published their timetable based on the time that their head office was working to. So Boston time, New York time, Philadelphia time, whatever. So these poor crossing controllers, or junction controllers, had, here's the clock to go with Boston with the Boston timetable, here's the New York clock with the New York timetables, and things like this. And they were like, this is a nightmare. So this is then what eventually gave us, moved us, whoops, I'm going to skip that one, moved us forwards towards time zones. So, time zones started off in the US. We had, in 1881, the US standardized into 4 discrete time zones. Rather than every town and every big organization having their own time, there was now just 4. You subscribed to one of those 4. A couple of years later, in 1884, we then had Greenwich becoming the global prime meridian, the time zero to which all other times are now measured. This meant that we had a global awareness of what time was. This allowed us to have synchronized consumption of radio and TV broadcasts, because you could now, for the first time ever, say, and come back at 9 o'clock tomorrow to hear what happens. That was not a thing before then. It was just kind of like, I wonder what's on the radio. Okay, whatever. Sporting events could be published to say, right, we're going to have a football match at 9 o'clock. Come and watch it. Until then, it was just kind of whoever was around at 9 o'clock played the match, and there wasn't really any spectators. So spectating at sports became a thing because we now had a sense of coordinated time. Modern time zones are a little bit strange. There is a lot of them. You would kind of think that there would be 24 of them. There's a lot more than that. Because there are certain countries who are just trying to sort of be the first country to be in a new day. So they are 14 hours ahead of Greenwich Mean Time. You have countries that are 12 hours behind, so we span a period of 26 hours with our time zones. And then we have ones that run on quarter or half hours rather than whole hours. So there is quite a few of them. Now, here we have all these different time zones that we can now factor in and think about what people are doing, know when people are talking about when they say, oh, I'll phone you at 9 p.m. or whatever. I'll skip that one. Moving into the 1900s, we then had the invention of the quartz crystal the quartz crystals were pre-existing, but to be able to use them as a timing device. Now, if you've hit a bell makes a particular sound. It makes a particular sound because any bell has its own natural resonant frequency. Quartz crystals have their own natural resonant frequency. 32,768 hertz. So that means it will go one way to the other way and back to where it started more than 32,000 times a second. That means we can start to measure things very accurately. We can start to measure things down to individual oscillations of a quartz crystal. Which gave us the problem that actually what we were able to measure was now more precise than what our definition of a second was. Okay? So we're measuring down to less than a 32,000th of a second. But how did we define a second? So how long is a second? Well, it was, divide a day by a solar day, by 24 hours, by 60 minutes, by 60 seconds, and you get, it's 1/86,400th of a second. But as I said, the orbit, the rotation rate of the Earth is changing. So I thought, right, as I said with the pendulums, you use a bigger number and divide it up more, you get a more accurate result. So I thought, right, we'll go for a year. So they went for the mean tropical year, and they ended up with a value of, it's 31,556,925.9747 of a mean tropical year. And we had a much better definition of what a second was. Better having a particular meaning. So it was better for those that wanted very precise measurements of time. So we then go forward in time, and we now have space. And we have satellites all over the place. The ones that people are probably going to be most familiar with would be the GPS satellites. I know this audience has a soft spot for the Iridium satellites that are almost all gone. I don't know if there's any of them left. And of course the International Space Station. But the GPS is a good one to be talking about. Because GPS, for it to work, needs clocks that are more accurate than those quartz crystals could provide. A quartz crystal is a little bit less than 1/32,000th of a second. GPS will only work if you have times down to billionths of a second. So it needed a huge upgrade in what we could actually measure. So this gives us the first foray into atomic time. So in the 1950s we invented atomic time. And that was like, yeah, this is great. This gives us a much better way of being able to measure time. And in 1967, we actually replaced what the definition of time was. A second was no longer defined in terms of the day or the year. It wasn't defined in astronomical terms. It was defined in atomic terms, which I'm just going to pull up on the screen because it's too much to say in one go. So the definition was that 9,192,631 hang on, got that wrong. 9,192,631,770 oscillations of the transition between two hyperfine energy levels of the ground state cesium-133 atoms, single outer electron shell from one energy level spin to the other. Okay. So, a bell has a natural frequency it will ring at. Electrons going around atoms have a natural energy level that they can sit at. And if they are spinning one way, they have a certain energy. If you spin them the other way, they have a slightly different energy, a very, very fractional amount of energy. And the energy difference between these, they will oscillate back. So if you excite it, it will come back down again more than 9 billion times in a second. So that, yes, we have a really accurate way of now measuring time. Now, it does say blah, 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 770. That's actually plus or minus 20 per second, so there is a bit of tolerance on that. But still, this is accurate to more than a nanosecond per month. The UK's atomic clock will be accurate to within 1 second for 138 million years. Okay, so that's pretty good. But this allowed us to have more precise GPS, to have more nuanced financial transactions, because we all love the financial transactions, to have more accurate scientific experiments. CERN would not be possible without atomic clocks. The Event Horizon Telescope, which timestamps all of its data with atomic time, would not work without this level of precision. If it wasn't able to go down to billionths of a second, we would not have those images that came out last week. But we want to go further. So, there is an upgrade that is being proposed to go for 100,000 times more precision. It's using an isotope of strontium. Now, both cesium and strontium are good because they're reasonably stable, so they're not radioactive, and they're not things that are going to be, explosive, carcinogenic, all that sort of stuff that we have to worry about. So using strontium, and you end up with, rather than microwave frequencies, which is what they have to work with microwaves to oscillate the quartz crystal, they can now use optical light. So this is why we can get to this level of improvement of 100,000 times faster. It would be accurate to 100 seconds over 14 billion years. This is the level of precision that they're now moving towards. Now, that's a lot. Hopefully it was understandable, but I'm going to end with one bit that's a bit more tricky. I'll be light, I'll be gentle. And that is, of course, GPS and relativity. So, got to get one slide of relativity in there. Special relativity. Special relativity doesn't make sense because we don't go fast enough to experience it. But if you travel at a substantial portion of the speed of light, time itself slows down. So these GPS satellites, which are going at 20,000 kilometers per hour around the Earth, are traveling so fast they have this effect from special relativity. So they slow down by 7 microseconds per day. But they're also really high in terms of the altitude away from Earth. That means they are at a higher point in the gravitational field. Now, gravity causes things to slow down. So if you were to fall into a black hole, your time frame would slow down. But they're further up, so their time frame is speeding up. So it speeds up by 45 microseconds per day. Those two balance out to give you 38 microseconds of difference per day. If that was not corrected for between a GPS reading now, today, and the same time tomorrow, would be 11 kilometers worth of difference. So, the atomic clocks that they put onto satellites have to know the orbit they're going to be at, and they tune those atomic clocks to measure the rate of time. So they can't change the rate it ticks, because that's the resonant property of whatever the atom or the quartz or whatever it happens to be that they're using. So all they can do is count the ticks, but change the scaling factor. How many of those ticks have to be put together to make a second? Now that's great, because if it's a scaling factor, that means it's a software thing, and if a satellite doesn't end up where you thought it was going to be, you just do an update, and you can change the scaling. So you can just change what the scaling is if it ends up at a different altitude above the Earth. So, atomic clocks have to factor in both special and general relativity to give us the accuracy of GPS. Without it, we wouldn't be able to navigate the way that we do. All of that is thanks to time.